Thank you. Thank you all for coming. Thank you for having me. And let's get right into it. So the chromatic symmetric function is a generalization of the chromatic polynomial. And to define that, we can start with the part of the talk that is actually my usual, which is about this much of it. So if you have a graph, then a k-coloring of the graph is just a function that assigns to each vertex a number from 1 up through k, with the constraint that on each edge, the two ends receive different colors. And throughout this talk, there will be a difference between a k-coloring, which has numbers 1 through k, and a coloring where you can use all of the natural numbers. And this is a slightly subtle difference, and usually you won't notice it, but I'm just pointing it out so that it won't confuse you later. And then the chromatic polynomial, called chi-g of a graph, is a polynomial that counts the number of colorings, in the sense that if you evaluate this thing at an integer k, let's say a non-negative integer k, then it's equal to the number of k colorings of g for all natural numbers. And so this is probably a thing you've heard of, and here are a few simple examples. If you look at a triangle and you count k colorings, then you should start at a vertex. You can give it k colors. For the next vertex, there's one color you can't use anymore, so now you have k-1 options. And for the third vertex, you have two colors that are already used up, right? You know these two colors are different, and so the last vertex has k-2 options. Whereas if you have 3 vertices and no edges, then each of them just has k options separately. And so the polynomial is k cubed, and you could convince yourself that for this graph, the claw, you have k options for your first vertex, and then say you start here, for each of the other vertices, you have k-1 options. And if you've heard of the chromatic polynomial, you probably have the first fact you know about it, which is a theorem that Tutt credits to Foster, and it's just that this satisfies a deletion contraction relation. Namely, if you look at this polynomial chi-g for graph G, it's equal to that polynomial with any fixed edge E deleted minus the polynomial with the same edge contracted, which is just owing to the fact that if you delete the edge, now you're counting all colorings, but also the two endpoints of the edge could now have gotten the same color. But if you contract the edge, that exactly counts those colorings where the two ends had the same color, so you get rid exactly of the stuff you overcounted in the first place. And this could be used to show that the thing is a polynomial, right? Because if you now do it for every edge in the graph runs out of edges. And what you're left with is just a stable set. And on the stable set, it's just x to the power size of the stable set, which gives us this theorem of Whitney's, right? If I want to know chi-g, I can just look at, for each subset of the edge set, what happens if I contract those edges and I delete all the others. Well, the size of the stable set I end up with is just the number of connected components I get in the graph if I just keep the edges in S and get rid of all the others. And so you get a -1 to the S because each time you contract, you get a -1 sign in this formula. But this tells you the thing is a polynomial. And later we'll actually see that this formula has a sort of analog for the symmetric chromatic function. So let's define the symmetric chromatic function. And basically the goal is we have the chromatic polynomial, it counts number of colorings, but let's be a bit more careful and count a bit more. Let's, for each coloring, actually count how many vertices are in each color class. So I have a function, xg, and now it's going to be an accountable number of variables, x1 and so on, indexed by natural numbers. And we define it just as a formal sum, as the sum of overall colorings, and here I mean colorings with natural numbers. And for each coloring, we get a monomial, which is overall vertices. You take one term that corresponds to x, sum the color that the vertex got, meaning that in a fixed coloring. If you gave 3 vertices the color 1, you get a term x1 cubed in this monomial, and so on for every other color, which seems way more complicated in the beginning, but it also contains more information. And this definition is due to Stanley, and here's a very simple example where we can explicitly compute the thing. If you look at this graph G over here, then you will see that essentially there are 2 ways to color it. You can give A and D the same color, or you can give them different colors. And essentially, up to renaming the colors, these are the only 2 things you can do. So we can count all colorings by grouping them into 2 categories. Are A and D colored the same or not? If they are colored the same, then I will get a term squared corresponding to the color that A and D are given, and 2 terms to the power of 1 corresponding to the colors of B and C. So this is just the sum over all terms where the indices J1, J2, J3 are distinct, xj1 squared, xj2, xj3. Right, so I'm just counting. There's 1 color that is given to 2 vertices, and then there are 2 colors each given to 1 vertex. And similarly, if A and D don't get the same color, I just get a sum where I have 4 different subscripts for my 4 variables. And since I told you about the chromatic polynomial, clearly the first thing we want from a generalization of it is to be able to do deletion contraction. But you can't, and the reason you can't is simple. If you look at this function, right, it's a sum with monomials here, but the degree of each monomial is the number of vertices of the graph G, which is fine if you delete an edge and not at all fine if you contract an edge. If you contract an edge, you just get something of an entirely different degree, and you can't hope to have any kind of equation that works here. So from a graph's point of view, the first thing to do is fix this. So let's fix this by giving weights to vertices, right? The only thing that hurts is just that when we contract an edge, we lost a vertex. But if we just remembered that the contracted vertex used to be 2, there isn't a problem. And that's the basis of this slight change, where I highlighted for you the parts that are now different, which is just we give a graph weights and remember them. And then instead of counting how many vertices are colored with a given color, we count the total weight. So for each vertex, we take x sub its color to the power of its weight. And this, makes sense, and it fixes the previous thing. Right, so, this is not a huge change so far, but it works now. We can apply deletion contraction, which is nice because it helps us prove lots of things. Right, so basically, first theorem, it works now. We fixed it just by saying there are weights, and we need to say what is the weight when you contract something, but when you contract an edge with ends u and v, then the weight of the new vertex should be the sum of the previous weights. Right, and now the proof I told you in the very beginning, if I count colorings of a graph with an edge uv in it, then the colors of u and v should be different, but if I delete the edge, I count both. The colors are different and the colors are the same, so I should subtract the ones where the colors are the same. Right, the same proof now actually works for this modified thing. And so I said this generalizes the chromatic polynomial, but it probably wasn't immediately clear how. And so this first theorem tells you how to recover the evaluations of the chromatic polynomial. Somehow it doesn't directly translate into you plug in these things and you get the polynomial, but at least you can recover what it evaluates to. And so the way you count the number of k colorings is you take our new polynomial xgw and you plug in k1s and then the rest all zeros. And then what happens is for each coloring, you count how many vertices are colored with each color, and if any one of them uses a color that's larger than k, that term goes away. And if you only use colors 1 up through k, the term becomes 1. So you counted exactly the number of K colorings, which is nice, but somehow not entirely satisfying yet, because we can evaluate Kaiji at different places, right? Not just at positive integers. In particular, Kaiji of -1 counts the number of acyclic orientations of a graph, but right here in this formula, you'd be hard pressed to plug in a negative number of ones into this formula. So there's still a bit of a disconnect there, right? We recover somehow enough information that clearly this determines Kaiji, but Kaiji also holds more information that we can't immediately read out of this thing yet. And now, before we fix this, this part so far covers how xg is a chromatic function. And now we're going to talk briefly about symmetric. And symmetric functions are an algebraic combinatorics thing that they're used for many different things. And here I'm going to say the bare minimum about them. So we say a function, and this is just any function on variables that are indexed by natural numbers, is symmetric. And here I use the very formula if it looks like a polynomial. So basically, if it's a formal power series of bounded degree and everything behaves well. And then also for every bijection of the natural numbers, if we plug in the variables in that order instead of the original one, it doesn't make a difference. Right, so it's symmetric because only the multiset of what we plug into it matters, but the order doesn't matter at all. And clearly XGW is symmetric because if F is a coloring and I apply a bijection to the colors, it's still a coloring. Right, so it's a symmetric function. And then one of the ways people look at symmetric functions is that they are vector space, and people look at bases. And so to look at bases, we kind of have to understand what information symmetric functions actually hold, right? So if I wanted to make the smallest symmetric function, it would be 0. If I wanted to make the second smallest symmetric function, I could say, let's take a term x1, but then because of this permutation property, I would have to have x1 plus x2 plus x3 and so on. And similarly, I could start with x1 squared, and then I would also get plus x2 squared and so on. I could start x1, x2, but then I would also need plus xi, xj for every pair of I and j that are distinct. So really, if you look at it, it's not that every monomial has a different coefficient, but that if monomials can be mapped to each other using this bijection between variables, then they have to have the same coefficient. And the monomials that can be mapped to each other are exactly those that come from the same partition, right? If I look at a monomial and look at the exponents, that's a partition of its degree. For example, for x1 squared, it's just a partition 2 of the number 2. And it can be mapped to every monomial where I get the same partition 2. And on the other end, for x1, x2, the partition is 1, 1, the partition of 2, and for every other monomial, that's xi, xj with ij distinct. It also corresponds to the partition 1, 1, and so the thing has to have the same coefficient. Which is a long-winded way of saying whenever the partition is the same, the coefficient has to be the same. So I can make a basis of this thing by saying, let's group together for one partition all the possible monomials I can make from it and call that m lambda. And now I can write every symmetric function as a sum over partitions lambda of m lambdas with some coefficient that corresponds to the shared coefficient of all monomials that have this partition as the pattern arising from its exponent. Where here I cheated a little bit because there are some multiplicity issues, right? If I sum over distinct things, I actually get two terms, x1, x2, because I get x1, x2, and x2, x1. But let us for the moment not worry about this too much. But that's the part that diverges from what the usual monomial basis is, which is why this is actually called m tilde, because it's slightly different to make things work better for us. But all of this is for a purpose, and the purpose is that now we can write the chromatic symmetric functions more compactly. Because if you look at the summation, it kind of looks like the summation we got when we first computed a chromatic symmetric function, right? We have a bunch of distinct things, and then we have here some product of variables. And in fact, it works like that, right? For this graph here, we send, if we color it, we have two kinds of ways to color it. Either all colors are distinct or A and D are the same. If A and D are the same, then we need one variable squared and the others each to the power of 1. So we generate terms that correspond to the partition 2, 1, 1. And if instead we color A and D with different colors, then all 4 terms have to be to the power of 1. So we have the partition 1, 1, 1, 1, and we generate all monomials corresponding to that. So we can rewrite xg for this graph as just the sum over those two things on the monomial basis, which is nicer and shorter, and it sort of tells you what the monomial basis does, right? We count not colorings, but we count colorings that are somehow fundamentally different, and for each of those we get a different term, where fundamentally different means they actually give us a different partition of the vertex set into color classes. And I like to think of things as graphs. So I like to think of the monomial basis really as the chromatic symmetric polynomial of a graph. And that graph is a complete graph with vertex weights. If you look at this term, it tells me that I have to use k different colors. And for each color, the total weight of vertices with that color should be lambda I for the different colors. So if you look at this, that just means I have a k vertex complete graph with vertex weights lambda 1 up through lambda k, and I'm coloring it, right? Because then I have to give k distinct colors, and for the ith color, I get weight lambda I. So we can not think of this as a symmetric function anymore, but instead let's think of it as a complete graph with vertex weights. And then I can say the colorings of this graph G that we've looked at before, well, they're just colorings of this complete graph where I have 2 vertices with weight 1 and 1 of weight 2, because I have to color with 3 different colors, but 1 is used with weight 2 and the others are only used with weight 1. Plus this complete graph where I use each color only once, so each vertex has weight 1. And so I can think of the spaces as graphs. And now something nice happens, which is if you look at this formula we've written here, this is actually the deletion contraction formula, right? If you look at this edge, then the graph on the left is the graph with that edge deleted, and here we have that edge contracted, and here the edge is still present. So, this agrees with deletion contraction, but also it allows us to not think of symmetric functions, but instead think of these things as graphs. And we already said, basically writing things in the M basis just amounts to coloring that are fundamentally distinct. And so formally, that means we can write xgw in the M basis by saying, let's sum over all stable partitions, where stable partition means a partition of the vertex set into stable sets, and then count M and the type of P, where the type is just the partition we get by taking for each part the sum of the weights of the vertices in that part. Or if we want to say it more concisely, the coefficient of xgw in this M lambda basis is just the number of stable partitions of G that have this type lambda. Right, so just to go back to the example, if we look at this graph once more, we can see it has two ways to partition it into stable sets because A and D can be in the same part or they can be in different parts, which gives us exactly 2, 1, 1 and 1, 1, 1, 1 as before. So far we haven't done very much, but it's one of the things that people do with this then is say, all right, let's look at different bases. Let's see what happens if we take this thing and write it in a different basis. And we're going to look at the first two, the P basis and the E basis, but there are lots of them. There's a homogeneous basis, which has terms that correspond to adding terms for all the partitions. The Schur basis, which seems to be related to representation theory. And they have a specific basis called the forgotten basis that I don't know what is, but I feel bound for. So now you know about it. And there are probably more that I haven't listed, but we're going to look at the first two because the first two are actually nice in terms of graphs. And this might be a theme you've surmised already. I like when things are nice in terms of graphs. And so to see what they mean in terms of graphs, here's a theorem that just says if I take the disjoint union of two graphs, right? So disjoint vertex sets, put one graph here, put one graph there, put no edges between, then what that means for the chromatic symmetric function is just that I'm taking the product of those two things. And the proof where for the dots you fill in all the definition is just if I count colorings of left and right, then I just count a left coloring and a right coloring and pairs of those things. And this formula is actually the same for chi-G, right? If you count colorings here and there, and just the number of K colorings, then you multiply how many do you have here and how many do you have there. So this makes sense, but also this tells us something about how things relate to graphs. If I'm multiplying chromatic symmetric functions, I'm taking disjoint unions of graphs. Which means now I can tell you what the P basis is. The P basis starts by defining it for the partition with just one part. So if I have just one part and it's K, then I'm just taking the sum over all I and n of xi to the k. Which means in terms of a graph, I just use one color, but that one color is given to a vertex of weight k. So this term pk is the chromatic symmetric function of the graph that has one vertex and the one vertex has weight k. And now for general lambda, I define p sub lambda as just the product of p lambda I for each of the parts of lambda. And as we saw in the previous slide, if I take the product of those things, then in graph terms, what I'm just doing is disjoint union. So much like we saw that the M basis corresponds to complete graphs, this P basis corresponds to graphs with no edges. And the vertices in that graph with no edges just have weights that correspond to the parts of the partition lambda. So the M basis gives us this thing, complete graphs with weights. The P basis gives us this thing, graphs with no edges, stable sets, and the same weights. So the M basis and the P basis are actually graph complements. And before we stop saying things about symmetric function bases, let's look at the elementary basis. And then we will say things about them instead of defining bases. For the elementary bases, and again, I put a tilde because I disagree with the standard definition by a multiplicative, like by a factor. But let's pretend this is the definition, then EK is just the sum over all indices J1 up through JK distinct, and then the product of just X sub JI. And if you've seen all the other formulas in this talk so far, this will look familiar as what I'm doing here is just I'm taking a K vertex complete graph with each vertex of weight 1 and coloring it, right? This is the chromatic symmetric function of a K vertex complete graph where each vertex has weight 1. And now to make the thing for lambda, instead of just for one integer K, I'm taking the product, which means I'm taking the disjoint union. So the E basis for E lambda is just the disjoint union of complete graphs. And this time, the parts of lambda aren't vertex weights, because all the weights are 1, but they are the sizes of the complete graphs that I take the unions of. So if I wanted to see what the term for 2, 1, 1 looks like, this is the graph you get, right? I have 3 complete graphs, one of size 2 and 2 of size 1, which makes this a very small example, but this is the graph whose chromatic symmetric function gives me exactly up to the tilde, the basis E211 term. And so now we can write chromatic symmetric functions in different bases, which are also graphs, which helps us because to compute how to write this chromatic symmetric function in these bases, we can apply deletion contraction to get to these graphs. Also, I said that the M's and the P's are graph complements, and sort of there's something going on here where it feels like we have 3 sides of a square because we have stable sets with weights, complete graphs with weights, and then we have disjoint unions of complete graphs, and clearly we should have the complements of these, right? If we have the M's and the P's, then the complements of the E's should be somewhere, and it would have been really nice if it was the forgotten basis, but it's not, as far as I know. But it is a basis that was introduced by Penaguayo, and he called it the R basis. We also thought about it and called it the B basis for basis, but R seems better for really interesting basis, right? So this is the R basis. And these are the ones that we'll look at. And so, right, basically now the question is, I have this complicated thing, it counts colorings in a hopefully better way. If I write it in terms of these other bases, what do the coefficients mean about the graph? Which is the question I conveniently wrote on this slide, right? If we take the chromatic symmetric function, which is an element of a vector space, and translate it to one of our many bases, do the coefficients tell us a fact about the graph? And we talked already about the M basis, and we said actually the coefficient of M lambda in XGW just counts the number of stable partitions, the number of partitions of the vertex set into stable sets that are of type lambda, meaning that the sum of vertex weights in each part is a partition of the total vertex weight, and that partition is lambda. So we actually are already a quarter done. We know the interpretation for these things that count stable partitions. And so somehow the M basis is really the one that tells us about colorings. The P basis is a bit different. But if you think about what we said in the very beginning about the chromatic polynomial, as we said, to prove it's a polynomial, take every subset of the edge set and see what happens if we contract these and delete the rest. And then what you get is a stable set where we know it's x to the k. And here we now also have this same principle. We can apply deletion contraction to every subset of the vertex set until we're left with a stable set. It has to have weights now, but we know what a weighted stable set is. A weighted stable set is just an element of the P basis. So we can compute this thing in the p-basis by just saying, let's apply deletion contraction exhaustively until all the edges are gone. And then here's what happens. For every subset of the edge set, you get a term that corresponds to contracting those, deleting the others. When you contract, you get a -1, so we get -1 to the s. And then what happens if we contract those, delete the others? Well, you contract each connected component of the graph with just the edges s in to a vertex, and the weight of that vertex is just the sum of the weights of the vertices in the connected component. So for this set S, by looking at connected components in the graph with just those edges and summing their weights, you know exactly which p lambda you will get here. Which Stanley, by the way, proved without deletion contraction. But our innovation to this theorem is we can add a W here, which I felt did not merit adding our names up here, which would have been a bigger change than our change to the theorem. But it's interesting, right, that there was a proof before deletion contraction that worked with symmetric functions, and that, you know, now there's a graph proof that I can tell you in just a few minutes. And the other thing that I like about this is that this looks exactly like the theorem of Whitby's that we looked at earlier. Right, so somehow the M basis counts colorings, the P basis seems to be the analog of this theorem of Whitby's. And so, given what you've seen so far, if you were very careful, you might have a guess as to what the E basis tells us. Also, I computed here the P basis for you, but it's somehow complicated, and I'm not sure what exactly this tells us about the coefficients, but this formula tells you how you can compute things in the P basis. The E basis corresponds to the other fact I mentioned about the chromatic polynomial, which is that evaluated at -1, it counts the number of acyclic orientations of a graph. And I said it's unfortunate that somehow we can't evaluate xg directly to recover this evaluation of chi g. But it's still in there somehow, and it's in there in the E basis, because if I have an unweighted graph, then I will look at partitions lambda of length k, where length just means the number of terms, right? The partition 2, 1, 1 has length 3, whereas 1, 1, 1, 1 has length 4. And if I sum over all partitions of the same length, the coefficient of the term E lambda in xg, and I also add this corrective factor, which I pay for defining the e's in terms of graphs instead of the normal way, then this sum counts the number of acyclic orientations of G with K sinks, where an acyclic orientation of a graph means every edge gets in a direction and I don't have a directed cycle. And then sinks are just vertices of at degree 0. And so each acyclic orientation has at least one sink, which is good because each partition has length at least 1. But this refines the result about chi g, where at -1 we just count all acyclic orientations, to saying now we can actually count them by their number of sinks. And this is due to Stanley, and there's a result of Bernardi and Nadeau that also relates evaluations at -j for j bigger than 1 to acyclic orientations and to the chromatic symmetric function that's less direct than this correspondence. But this tells us that we can somehow recover this acyclic orientations fact from the E basis, although it's not entirely clear to me how the E basis corresponds to plugging in -1. But it's there and it's nice. And you'll notice this is an unweighted result. We do have a weighted result, but the weighted result I summed up with you with a drawing, so I wouldn't have to explain all the words of it. Basically, the drawing tells you the previous thing analyzed acyclic orientations according to their number of sinks, but what if we have vertex weights? If I have a vertex of weight k and he's a sink, is he one sink? Is he k sinks? And this theorem answers this with neither. In fact, he can be any number of sinks from 1 up through k. Specifically, he can choose a subset of the numbers 1 up through k, and he can be sinks for that subset and not the rest. And so this tells you an interpretation for the same sum we saw on the previous slide, which previously was the number of acyclic orientations with k sinks, but in a weighted graph, it's a bit more complicated based on the fact from this drawing that vertices of weight k are not exactly sure how many sinks they are supposed to be. And so I added the fourth side of the square, the R basis, and that's something we're working on. It would be nice to see if this is also a fun fact about chi G somehow. Maybe there's something else we can connect it to. Clearly, if we're just completing things, right, we looked at the M's, which are evaluations and positive integers, and then the E's had to do with negative integers, and clearly the R's are what happens if we plug in complex numbers. And let me stop giving you ideas here that are probably not based in truth, but another thing that happens with the R basis is that we looked at the P's and the E's, and lots of stuff happened there with disjoint unions. The M's and the R's are actually compatible with the opposite, taking two graphs and putting all edges between. So they are compatible with complete joins, and in terms of algebraic combinatorics, they correspond to two different products in the ring of symmetric functions. So there should be something interesting there, but we don't know it yet. And so what I want to tell you about now is basically what are the questions that people have about this. And we looked at the first one, what do the coefficients mean? And for the E basis, the elementary basis, you'll have noticed we looked at sums over all partitions of length k, and we had an interpretation for that sum. But for the M's, we actually could say something about individual coefficients, and the same sort of for the P's. So why can't we do it here? And the reason, well, the possible reason is that combinatorial interpretations usually require things to be something you can count, and so we would like the coefficients to all have the same sign. In particular, we would like them to all be positive, but they're not. And if you don't want to listen to my words for the next 2 minutes, you can check that this calculation of the E coefficients for the claw is correct. But more to the point, for the claw, the E coefficients are actually not all of the same sign. There's this particular last one here, E22, which is negative, which means when we're counting the number of acyclic orientations, since 2 has length 2 and 3 has length 2, there's actually a cancellation. If we sum their absolute values, we would not be counting the number of acyclic orientations with some number of sinks, but something cancels here, which is strange, and which means we don't really know how to relate this to acyclic orientations yet. So instead, people looked at, when does that happen? Maybe the claw is the only problem, the only case where this has a negative coefficient, and there's an example of Kahn's that says, well, no, there's another one. This one, called the net, also has a negative E coefficient, which led to the Stanley-Stenbridge conjecture, which is one of the main conjectures people are working on in this field, saying if G is claw-free and unweighted, we are assuming from now on, and an incomparability graph, then XG has non-negative coefficients in the E basis. The reason for saying incomparability graph is that the net is neither a comparability graph nor an incomparability graph. So by going to incomparability graph, you get rid of the net. And Guy Paquet actually proved that we can reduce this further. It would be enough to prove that xg has non-negative coefficients in the E basis for unit interval graphs, which from a graph perspective seems outrageous because those things are so easy to color. Clearly, we should be able to say something about this, but as of yet, we can't. And the other thing is there's a conjecture that maybe we don't need to be so restrictive as to go to incomparability graphs. Maybe those two, the claw and the net, are the only two problems. And maybe if G doesn't contain either of them, then xg has non-negative coefficients in the E basis. And you can tell from this conjecture that some of these people are graphs people and they would like an induced subgraphs result about this. Right, this claw-free and net-free is an induced subgraph statement now, which I guess makes this the second part of the talk that is in my usual wheelhouse. But even this one for unit interval graphs seems so, easy if we just look at it in terms of graphs, but it's not. Unless you go ahead and fix it after this talk, then please let me know. The other thing people care about is, well, we're counting things better now. We know that chi-g, the chromatic polynomial, is not very good at distinguishing graphs, but maybe xg does. And so this is not true, and that example, the first example is due to Stanley. If you look at these two graphs, you can convince yourself that they are not, in fact, isomorphic. But if you look at the red edge and you contract it, you get, in both cases, this weighted graph where weights 1 are omitted, and I just wrote the weight 2 where the weight is 2. And if you delete the red edge, you get this graph. So since contracting the red edge makes it to the same graph and deleting makes it into the same graph because of the deletion contraction relation, we know that xg on those two graphs is in fact the same. So xg does not distinguish all graphs, which maybe is okay. We kind of expected it, so let's be more careful and say which graphs might be distinguished. And so there are constructions for infinite families of pairs of graphs with the same xg, so it's not like the claw and the net that we can hope there's just two problems and excluding those makes everything better. And many of these constructions initially had triangles, right? If you look back to the previous example, one thing that we actually benefited from was doing contraction and then getting rid of double edges. And this somehow uses that this thing has triangles, which cancel different double edges in the different pictures. So maybe triangles were the problem, but in fact, now we have examples that have large girth, which leaves only one possible conjecture, which is due to Stanley and says this thing distinguishes trees. And now again, if you come at this from a graph's perspective, you should say this is absolutely outrageous. Chi-g is the same for every tree. How can this be your conjecture? How can this possibly be true when we know that chi-g is especially bad at distinguishing trees? It might distinguish some other things, but it definitely doesn't distinguish trees in the slightest. But this conjecture is also still open, and I think it's been computer checked up to trees of size 29 or something. Also, there's a historical inaccuracy where this is attributed to Stanley as a conjecture, but he actually just wrote, "We do not know whether xg distinguishes trees," a statement that is definitely true. And so since this is a Matroid seminar, here's the obligatory slide on Matroids. It would be nice to have a generalization of this for Matroids, and as the Matroids people presumably know, there's a chromatic polynomial for Matroids, which is usually called the characteristic polynomial, and it is the same as the chromatic polynomial for graphs if your Matroid comes from a graph up to a factor of x, because here we're looking at the rank of the whole Matroid minus the rank of a set, which is the number of connected components of the graph minus 1 if it's a graph, which I like to pretend everything is. And so the characteristic polynomial is somehow the exact analog of the chromatic polynomial for graphs. So why doesn't the chromatic symmetric function have a matroid analog? And there are some definitions, but they're somehow not exact analogs. And, you know, deletion contraction stuff seems like a very natural thing to bring to matroids. There's this small problem that somehow matroids also don't distinguish trees very well. But since many of you are interested in matroids, please fix this. Can you formulate an analog of this that works for all matroids? I would be very grateful. And before I end, let me advertise that Logan will be talking about this in the algebraic combinatorics seminar, giving a more true and honest account of the algebraic combinatorics side of this. So if you want to hear more about this, it's in the Waterloo Algebraic Combinatorics seminar on September 17th. And with that, thank you, and let me know if you have questions.
Thank you, Sophie. Are there any questions?
Well, I did have a comment.
All right.
So you mentioned at the end there something like matroids don't distinguish trees very well. Actually, it's very easy to use binary matroids to distinguish trees.
Okay.
So if you take the adjacency matrix of a graph, a simple graph, and you put an identity matrix in front of it, then you get a representation of a binary matroid with twice as many elements as the graph has vertices. Mm-hmm. And that matroid classifies trees up to isomorphism.
Oh, that's nice. So maybe that's the one that should have an analog for this.
Well, considering that that matroid is vertex-based, it
Yes.
makes sense that it has some connection with partitions of the vertex.
Thank you. I'll have a look and see if maybe that's the right thing to generalize to this.
Sure, and if you're interested, you feel free to drop me a line.
I will, thank you. There's a comment in the chat. Yes. So the contraction deletion formula follows from lots of things. Basically, this chromatic symmetric function is known under different names to different people, and yes, other people have also defined weighted versions of it before and known that there is a deletion contraction relation. So this is not entirely news, and not entirely news that it exists for the chromatic symmetric function. But our version seems to work nicely to make graph-based proofs work. But yes, thank you for pointing it out. Maybe Logan can say who has the corresponding U polynomial thing. Although I made him mute himself, so maybe he doesn't hear.
There's a comment from Logan there.
Yes, he says the weighted, so I lied. I made this based on the chromatic polynomial, but really it should be based on the Tut polynomial, which also has an analog, which is the band coloring symmetric function, or the Tut symmetric function. And these have equivalents coming from somewhere else called the U and W polynomial. And one of them has weights and also has deletion contraction. So yes, lots of these things are also known by different names, and lots of the results somehow translate. And it's hard to find all of it, so I tried to give you the most streamlined introduction that makes sense in terms of graphs, but I certainly lied about many things. Somebody asked what information about the graph we can recover, and that's a good question. Certainly there's some easy stuff you can say, like you can figure out the total weight, and let's say the thing is unweighted, you can also figure out the number of edges. And since people care about trees, there are some things in trees that people know can be recovered. A thing called the subtree polynomial. There's lots of this that people study. And recently we've also been looking at XB, the TUD analog of this, and you can ask what things does this distinguish? Maybe adding the additional information that the TUD analog gives us now distinguishes everything, but it doesn't. And for trees, the TUD and this one are the same. But yeah, the complete answer to how much can we recover isn't known. But for the TUD analog, we can recover more things like the degree sequence and stuff, which I'm not sure we can from XG, but Logan, correct me. And somebody asked about how is the number of sinks defined? This I can answer. So instead of counting acyclic orientations, we're counting pairs of acyclic orientations and maps S, where S is a function that assigns for each sink a non-empty subset of the set 1 up to the weight of the sink. So each sink can be any subset of 1 up through its weight, actual sinks. And then the length K of the partition that we're counting here corresponds to the sum over all sinks of the size of the subset that we assign to be the actual sinks within that vertex. And we count pairs of that, and then there's a bunch of adjusting the sign, which is we have the total weight of the graph and adjust against the number of vertices, and then we have the total number of sinks in the sense that we count these subsets and make a subset of that be the actual sinks versus the real number of sinks of gamma forgetting about weights. And this coefficient, well, the sum of coefficients gives us the same sum over pairs of acyclic orientations and assignments of which parts of the sinks are actually counted as sinks that add up to the right total number.
Are there any more questions? Well, if not, then thank you again, Sophie.